In this series of videos, we're going to talk about periodic trends. And I always like to start discussion of periodic trends with a discussion of 4 simple species, which illustrate all of the fundamental concepts that we need to understand in order to be able to predict and understand periodic trends. And those 4 species are the hydrogen atom, which has 1 proton and 1 electron, the hydride anion, which has 1 proton in its nucleus and 2 electrons, the helium cation, which has 2 protons in the nucleus and a single electron, and the helium atom, which of course has 2 protons and 2 electrons and usually some neutrons as well. So if I start by looking at hydrogen, which has 1 proton, so an atomic number of 1, it also has 1 electron that is moving around all around the atom like a crazy thing because, of course, Heisenberg's uncertainty principle says we can't know exactly where that electron is. If I add a second electron to the hydride anion, I'm now going to have 1 electron moving around like so, but I'm also going to have a second electron in that orbital traveling around the nucleus as well. For my helium cation, I have 2 protons in the nucleus, so my atomic number is 2, but I still only have 1 electron, and it's moving around all over the place like a crazy thing, just like so. And then in neutral helium, we also have 2 protons in the nucleus and our electron moving around all over the place, and a second electron also in that same orbital. So when we talk about periodic trends, the questions that we're going to be asking ourselves are things like, which of these species is biggest? Which of them requires most energy to take an electron off of? Which of them is easiest to add an extra electron to? And all of those questions can be answered by looking at how strongly is the electron attracted to the nucleus? How much positive charge does the electron feel coming from the nucleus? Because the size of the atom is dictated by the average distance from the nucleus to the outermost electrons. And if these electrons are held tightly, that'll be small. If the electrons are held loosely, the atom will be big. If the electrons are held tightly, it will take a lot of energy to remove one. If they're held loosely, it won't require very much energy at all. And so what we need to ask ourselves about each of these species is, how much positive charge does the electron actually feel coming from the nucleus? Now, in the case of the species which only have 1 electron, that question's pretty easy. There's only 1 electron. It feels the whole positive charge of the nucleus. And so the effective nuclear charge, which is what we call how much positive charge does the electron feel coming from the nucleus, is equal to the charge of the nucleus. So the effective nuclear charge on an electron in a hydrogen atom is 1. And the effective nuclear charge on an electron in a helium cation is 2. But what happens when you add a second electron? How does that charge get affected? Well, oftentimes some students suggest that in the hydride anion, because there's +1 coming from the nucleus and 2 electrons, that those 2 electrons should each get half of it. But that's not exactly how it works. What we have to think about is where the electrons are in the atom. Now, some of the time, the 2 electrons are going to be on completely opposite sides of the atom, in which case they're both going to feel the full +1 charge coming from the nucleus at that instant in time. But electrons are constantly moving. So maybe this electron flies over here, and now it's between the other electron and the nucleus. Well, now it's feeling the full +1 from the nucleus, but the other electron isn't anymore because the inner electron is blocking that charge. So the outer electron is now not necessarily feeling much of any charge from the nucleus. But the electrons keep moving, and they travel around, and some of the time one's blocking the other or shielding the other, because the formal term for this is shielding. And Some of the time it's being shielded by the other. And some of the time they're on opposite ends of the atom. And so we can't say exactly what our effective nuclear charge is, not based on this hand-waving qualitative description, but we can definitely say that the amount of positive charge that is being felt by either of those electrons is going to be less than 1. Neither of them is feeling the full +1 charge from the nucleus because it's always shielded some of the time. But it should be greater than 0 because there is always some of the time when it's not being shielded. Now, if we apply the same logic to the neutral helium atom, we draw fairly similar conclusions. We have 2 electrons, and some of the time they're on completely opposite ends of the atom. So that means that they would then each be feeling the full +2 charge from the nucleus. But some of the time, one electron is completely shielding the other. Now, an electron has a charge of -1. It can only shield 1 unit worth of positive charge from the nucleus. So in this instance, the outermost electron is feeling potentially +1 from the nucleus. But that's one instant in time. The electrons are both constantly moving. And so if the lowest amount of charge the electron could ever feel in any particular set of relative positions is 1, we know that the effective nuclear charge is going to be greater than 1, but it's going to be less than the full +2 charge of the nucleus. And so now we've been able to assess rough estimates of how much positive charge are the electrons in each of those species feeling coming from the nucleus. Now let's use that to answer some questions. Which of these should be biggest? Well, the biggest one is going to be the one in which the electrons are held least tightly to the nucleus. So the one in which the effective nuclear charge is the smallest. And looking at these 4 options, the biggest one is going to be the hydride anion because it's the only one in which the valence electrons feels less than +1 charge coming from the nucleus, in which there is an effective nuclear charge less than 1. So this is going to be the biggest. It's going to have the largest radius of the set of 4. Which one is the smallest? Well, that's going to be the helium cation because the electron in the helium cation is feeling the strongest pull to the nucleus. It's feeling an effective nuclear charge of +2. What about the others? Well, we have our biggest as the hydride anion, and we have our smallest as the helium cation. Between the other two, the effective nuclear charge on the helium atom that is neutral is larger than on the hydrogen atom, and so we would expect the hydrogen atom in which the electrons are being pulled less tightly to the nucleus to be bigger, and so we would expect to see the radii decreasing from hydride down to hydrogen, down to helium, down to the helium cation. Next question. Which one is easiest to grab an electron off of? Well, that's going to be the one in which the outermost electrons are held least tightly, in which we have the lowest effective nuclear charge. I will erase these to minimize confusion. And so the one that is easiest to remove electrons from is again going to be the one with the lowest effective nuclear charge, the hydride anion. So that's going to be the one that is easiest to remove electrons. And then, as you can imagine, the one that will be hardest to remove electrons from will be the helium cation, because that is the one in which the electron is held the most tightly. And of the two neutral species, the helium is holding its electrons more tightly than the hydrogen is, and so it has a higher effective nuclear charge and will therefore require more energy to remove the electron from. And so there is our ionization energy trend for this series. The last question asks about adding an electron. So hydrogen starts off with 1s1. If we add an electron, we're going to 1s2. So the next electron goes into the same subshell as the first electron was in. The same is true for the helium cation, 1s1 going to 1s2. On the other hand, for the helium anion and for the neutral helium molecule, if we add an electron, we're actually going to have to start a whole new shell. So 1s2, 2s1, and this would be 1s2, 2s1. It is never favorable to add a new electron if it has to go into a whole new shell of electrons. If you have to start a new shell of electrons, that's not a good thing. And so we cannot add another electron to either helium or the hydride anion. You can't make hydrogen with a -2 charge. Between the other two, we could potentially make H-. It's one of our other examples here. And we could potentially make neutral helium, which is going to release more energy, which is going to be easier to do. Well, it's going to be easier to add the electron to the species that has the most effective nuclear charge that will be felt by that new electron. It's better to add an electron where it's going to be strongly attracted to the nucleus. And the helium cation has more protons than the hydrogen atom does. That new electron will be more strongly attracted to the nucleus, and therefore the easiest species here to add an electron to is the helium cation. And so as you can see, all three major periodic trends, and I've just summarized all three of them, are controlled by effective nuclear charge. How much positive charge from the nucleus reaches the outermost